Alright, here we go. So chapter 3. So I probably put this stuff in your note card. So this first little box is kind of a review of the section. So 3.1 was pretty easy, just terminology. I'd know what this is. So the probability of A prime, that means the complement. So it's the chances that A does not happen. So if the chances of A happening is 20%, the complement would be 80%. So there, they've got to add and give you 1. This is pretty straightforward. The sample space is always going to be somewhere between 0 and 1. 0 including 0 and including 1, so 0 and 100%. And this guy we're going to use, this is pretty handy. Because if I want to solve for the probability of A and B, so that's the probability of A intersect B, I should use that instead of the AND word. If you times both sides by the probability of B, times this side by the probability of B, so the intersection is equal to the probability of A given B times the probability of B. So this formula comes from this formula, and they're pretty handy. Okay, so here we go. 3.1. Let's do all of chapter 3. Okay. So these are from your textbook. So these are the homework. I just picked a handful of homework assignments that are really good from the text. So 3.1, if you go through 24, 27, we'll go through a few of them. Use the following information to answer the next 10 exercises. On a baseball team, there are infielders and outfielders. Some players are great hitters, some players are not great hitters. So I is including those that are infield, O is outfield, H is a good hitter, N is a bad hitter. So here we go. 24. Write the symbols for the probability that a player is not an outfielder. If it's not an outfielder, you got, maybe if they're only classified by these two, you could assume if he's not an outfielder, he's an infielder. So you could go like probability of infielder, but I think what they're hinting at is not an outfielder, is the probability that it is the complement of an outfielder. So I think that's what they're after. 25. Is an outfielder or is a great hitter. So chances that he's an outfielder, that's O. Or is going to be the union, and a great hitter is H. So or is union, you gotta remember that. Or is union and is intersection. Okay, number 26. What are the chances he's an infielder and is not a great hitter? So and is the key word, so it's going to be probability that he is an infielder, that's I, and is intersect, not a great hitter, is N. Pretty easy. Let's do, okay, the next one. Write the symbols for the probability that a player is a great hitter given that, and that's conditional, that's this vertical bar thing, given that the player is an infielder. So what are the chances he's a great hitter? That's H. Given that is this vertical bar, the player is an infielder. Okay, and so on and so forth. So let's see, let's skip. We're going to save time because they're not bad. Maybe 34. What's the word for the set of all possible outcomes? That one is called a sample space. That includes every imaginable scenario. 35. What's conditional probability? We just did it. It is the likelihood of something happening given that something else has already happened. So the chance of something happening given that something has already happened first. Okay, so 3-1, kind of the terminology not bad, and interpreting this graph is really not too bad. So you've got 1,045 people who are sampled. 40% of the people approve, 60% do not approve, and then they kind of break it down by age groups, and then they've got them broken down by gender. So male, 478 of those 1,045 were male, 567 were female, 44% of the males approve, 56% of the males disapprove. Okay, so F, out of the females, so this is conditional, it's reducing the sample space. We're not looking at all of these 1,045. Given that the person is a female, what percent disapprove? So you're only looking at the females. You're only looking at these 567, and these are percentages. So 63% disapprove. Okay, look at G. Out of all the age groups, what percent approve of Mayor Ford? So all the age groups, we're looking at the whole sample, and it looks like 40% approve. So far those two are pretty easy. Okay, H. It's kind of the same wording as F, but the mathematical notation lets us condense this sentence into just easy notation. Find the probability that they approve given that they're a male. So you're only looking at this subset right here, the males, and 44%. I, out of the age groups, what percent are more than 44 years old? Okay, this one might be the hardest so far. More than 44, so that means they are in here. Okay, so here's what you gotta do. You gotta take these kids, 226, these kids, 268, these kids, 331, and you've got to add them all up. So we got to figure out how many are older than 44. So 14, 15, 6, 7, 8, 9, 10, 11, 12. So 825. So now we're going to do 825 are older than 44. If you divide that by the total, that'll give you the percent. So 825 out of 1045, it's like 79% or something. And J, find the chances of you randomly bumping into someone and they approve given that their age is less than 35. So the age is less than 35. That is going to be this subset right here. And the chances they approve, these 82 people, 30% approve. So 30% chance. Okay, that was 3-1. Now 3-2, we introduce independence and the idea of mutually exclusive. So read through this, and there are 3 ways to test for independence, and they're all right here. So I'd maybe put this in your notes. Here's how you test for independence. And they are independent if any one of these 3 works. So mutually exclusive, they cannot exist at the same time. They cannot have any overlap, no intersection. So their intersection is got to be 0. Okay, so here we go. Now, they're going to give you some information. Let C equal taking an English class. Let D equal taking a speech class. Suppose the chances of you taking an English class is 75%, speech class is 30%. Chances of you taking an English class given that you're taking a speech class is 75%, and the chance that you take them both, so an intersection, is 23%. Alright, so here we go. Are C and D independent? Well, we could use this guy. So the chances of C happening are 75%. The chances of C happening given that D happens is also 75. So the event D had nothing to do with C. So they both, chances of C happening is both 75%. So the answer is yes. So taking a speech class did not influence at all taking an English class. So that's one of the three, so that works. We're good. We don't need to test all three, just test one of them. Okay, are they mutually exclusive? Mutually exclusive? No, because of this. There is an intersection. 23% of the kids are taking both at the same time, so there's no way they're mutually exclusive. Now C, what are the chances of taking a speech class given that you're in an English class? And if you look up here, that's not given, so we gotta kind of find that ourselves. So now we're gonna go back and use from 3-1, we're gonna use this trusty formula right here. Boom, 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 boom. So we're gonna use this guy. Now, let's see where we are. Okay, so the chances of D happening given that C happens. That is actually the same thing as the intersection. So chances of D intersect C divided by the chance of C happening. So here we go. The intersection is 0.225, and chances of C happening all by itself is 75. So if we do that, we're gonna get, we get 0.3, which is what we hope to expect. I mean, we really didn't need to do this because if they're independent, we know this. The chances of D happening all by itself are 0.3, so it's 30%. And if they are independent, which we said they are in A, the chances of D happening given that C happens, C's not going to influence D, D's not going to influence C, it's going to be the same, it's going to be 30%. But we just proved it using this formula, and we're going to get the same, you're going to get 30%. So I guess we didn't need to do the work. If they're independent, D happening given C happens is the exact same as D happening all by itself. That's the beauty of independence. They do not influence each other at all. Okay, let's look at this guy. Student goes to the library. B is the event that a student checks out a book. D is the event a student checks out a DVD. Okay, now this one, check this out. This is kind of fun. We can, some of you, it's going to be way easier to visualize it maybe with a Venn diagram. So on a Venn diagram, they're pretty cool. They work just the same. So B is a book. We'll call the kids that live in this space book checker outers, and the kids that live in this space is DVD checker outers, and there is an intersection. So this overlap, there's 20%. Alright, so the chances that you run into a kid that checked out a book is 40%. So 20% live here, 20% live here. Chances of them checking out a DVD is 30%. 20% of them live here, so 10% of them live here. So now I've got 20, 40, 50. That means 50% of them live elsewhere, out in the universe. They checked out neither. Maybe they checked out a magazine or something. Who knows? Newspaper. Okay, so now let's just do it strictly with the Venn diagram instead of what we did last time with those formulas. Okay, A. What are the chances that you run into someone who checked out a book given that they live in the DVD world? Okay, if they live in the DVD world, this changes the sample space. All we're looking at is this DVD world. You're not looking at the entire 100%. We are only looking at 30%. Okay, so the chances they checked out a book, here's the book kids right here. So the chances are 0.2 out of 0.3. So it's 2/3. Okay, so A is 2/3. B, what are the chances that they have checked out a DVD given that they live in the book world? So now you're just looking at the book world. So the book world is right here, and looks like there's 40% of the kids living there. So what are the chances of those 40% that they checked out a DVD? These guys right here. So it is 0.20 out of 0.40. So that's going to give us 1/2, so 50%. Okay, are they independent? Hopefully we're going to say no. Because B just kind of proved it. So the chances of them checking out a DVD, given that they checked out a book, that was 0.5. And that should be the same as them checking out a DVD all by themselves. And checking out a DVD all by themselves with nothing, that was 0.3. So because 50% and 30% are not the same, the answer is no. So these do kind of influence each other a little bit. Are they mutually exclusive? The answer is no, because there is some kids who can check out both at the same time. So mutually exclusive can have no intersection. Okay, so the Venn diagram's kind of nice. Let's look at the next one. Okay, in a box there are 3 red cards, 5 blue cards. Red cards are marked with numbers 1, 2, 3. Blue cards 1, 2, 3, 4, 5. Cards are shuffled up. You reach into the box, you can't see, you draw one. R is the event, you draw a red card. B is the event, you draw a blue card. And E is the event, you draw an even numbered card. So here's the sample space. Looks like you got 1, 2, 3, 4, 5, 6, 7, 8. Oh, it's got it right here. 8 different outcomes. Okay, what are the chances you reach in and grab a red card? Well, 3 out of 8. Blue cards, 5 out of 8. Even cards, 1, 2, 3 out of 8. Okay, so those are easy. Now let's get into this funky business. So what are the chances that you reach in and you grab a red one and a blue one? And that should be 0. So these are mutually exclusive. You cannot grab one card and it come out being red and blue. It is either red or it is blue. So these are mutually exclusive. Okay, what are the chances that it's blue given that it's even? Okay, so now you're only looking at the evens. So you're only looking at these 3. So your sample space is out of 3. So what are the chances of those 3 cards that it was blue? Well, 1 is red and 2 are blue, so it's 2 out of 3. What are the chances that it's going to be even given that it's blue? Okay, blue, there's only 5. So here's the 5 blue, and out of those 5, we're looking for the even ones, so there's only 2 out of 5. Okay, now, are these independent? Okay, let's check real quick. So we're going R and E. So the chances of R is 3 out of 8. Let's do the chances of R given that it's even. And if it's 3 out of 8, we're in business. If it's not, no. Okay, chances of R given that it's even. We didn't do that. We're going to calculate ourselves. So even, there are 3 and only one of them. So that's 1/3. Okay, and 1/3 is not the same as 3/8, so they are not independent. How about mutually exclusive? Is there any intersection? Can they exist at the same time? Yeah, this one is red and even, so that's also a no. Okay, last one. Are the events red and blue independent? We just did this. Red and blue, they are mutually exclusive. That's a yes. Independent. Well, look. Dun, 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 dun. Ooh, that's a good question. I might have to think about that. Are they independent? So let's test these three things real quick. Chances of red all by itself are 3 out of 8. Chances of red given that it's blue, that's 0. So that's, I think we're going to go no. Okay, because this does not exist and this does not exist. Chances of red and blue, that can't exist. So we're going to go no, no on everything. Okay. Let's look at this guy right here. In a particular college class, 60% of the students are female. 50% of all students in the class have long hair. 45% of the students are female and have long hair. Of the female students, 75% have long hair. Ooh, a lot of information. F is the event that a student's female. L is the event that a student's got long hair. One student's picked at random. Okay, let's do this. Let's do both. Let's do a Venn diagram, and let's use the formula. And then we'll see that they're going to give us the exact same thing. Okay. Oh, actually, all they're asking is, are these independent? Oh, okay, so look, all that information is right here. Paching, pachang. I thought these were questions. So this is just in words. Here it is in math. So look at that. The math is way easier to understand than the words. That's the beauty of math. Okay, so it's just asking, are these independent? Well, gosh, I'm gonna look here and here. That's a no. Chances of you having long hair is 50%. Chances of you having long hair, given that you're a female, is 75%. Those are not the same. So it's gonna be a quick no. We haven't tested this guy yet. Let's test this one. So the intersection, chances of you being a female and having long hair, is 45%. If they're independent, that's the same thing as the chances of you being a female times the chances of you having long. So female is 0.6 times long is 0.5, and 60% times 50% is not 45%. So it's definitely a no. So actually this is a way quick question, but there's looked like it's going to take a long time. Okay, let's move on. Okay, this next one. Mark is deciding which route to take for work. His choices are the interstate and 5th Street. God, that probably should not be an and. That should be a or. I think that's a bad question. So I think they want him to have two different choices. He can either go the interstate or he can go 5th Street. Okay, let's see what the question. Chances of him going on the interstate are 44%. Chances of him going down 5th Street are 55%. So he goes down 5th Street more than he does the interstate. So what are the chances of him going down the interstate and 5th Street? Yeah, I'm pretty sure that's a typo. This has got to be 0. Because he's not going to take both routes to work. He's going to take either one or the other. What's the probability of him going on the interstate or 5th Street. Well, he's got 44% interstate, 55%. So it looks like we've got 99% chance that he takes one of them. So he's got a 0.1% chance that he takes some scenic route or some other route. Okay. Now, what are the chances of him going on the interstate given that he chose to go the freeway? And that's going to be 0. Because if he's going the freeway, he's locked in the freeway the whole time. He's not going to, or 5th Street, he's not going to ditch it and go on the interstate. So are these guys independent? No, because the chances of interstate are 44%, and the chances of interstate given the freeway are not 44%, they're 0. So the freeway, or 5th Street, is definitely influencing interstate. So that's a big no. Are they mutually exclusive? That's a big yes. There's 0 overlap. It's one or the other. Okay. So the last section in chapter 3 was 3.3. There's 2 basic rules of probability: multiplication and addition. And the multiplication, we've seen this. So the conditional formula is this: probability of A given that B happens is equal to their intersection divided by the probability of B happening. So these 2 formulas are the same thing. They're just algebraically manipulated a little bit. And the addition rule, or is easy. You just add them up, but then you've got to subtract the intersection. You got to always subtract the overlap, the stuff counted twice. Okay, so this is not bad. 3.3, here we go. Are the hits being made by Hank Aaron and the double independent? So it's multiple choice, A, B, C, D. So Hank Aaron, here we go. These are Hank Aaron's hits, and these are the double hits. Okay, so the chances of it being a Hank Aaron hit, he has got 3,771 of them out of the total 12,351. The chances of it being a double hit are 1,577 out of the total 12,351. So are they independent? Well, I guess before we do anything, we can look at the multiple choice. So it's either yes or no. Yes, because the chances of Hank, given that it's a double, are the chances that it's hit by Hank. Okay, let's find that. So the chances of Hank we already got. So let's find the chances of Hank given that it is a double. So now you're only looking at the double. So you're reducing the sample space. You're not looking at all 12 grand. You're only looking at the doubles. So that is 1577. So the chances of those 1577 that it came from Hank is 624. So is the chance of Hank the same thing as the chance of Hank given that it's a double? And that is no. If you punch them in a calculator, they will not reduce to the same thing. So that is a no. So it's not a yes, it's a no. So is it B or C? No, because the chances of Hank given a double is the same as a double. And chance of Hank given it's a double is... Okay, so look, there's a very subtle difference between B and C. B says this: chances of Hank given a double equals the chance of it being a double, and that's not what we're looking at. The chances of Hank given it's a double have got to be the same as the chances of Hank. So H is first, H first. So we're gonna go with C. Okay, number 98 from your homework. At college, 72% of the courses have a final exam. 46% of them have a research paper. suppose that 32% have a research paper and final exam. Let F be the event that of course has a final exam. Let R be the event that of course requires a research paper. Alright, so now check it out. This one's cool. Let's do both. Let's do a Venn diagram. So final and research. And you can do a Venn diagram because I know this. I know the intersection. 32% of the courses have both. Should have written bigger. Okay, 32% have both. 72% have a final. So I'm going to do my 72%, subtract my 32%. It should just be 40%. The research, 46% have research, so what's 46% minus 32%, and that is 14%. Now 40%, 32, that's 72, plus 14 is 86. So that means 14% are lucky and they have neither. Okay, so find the probability that a course has a final or a research. So you got to take the final, 72%, plus the research, which is 46, but you got to subtract these double counted. You have to subtract the intersection. Subtract 0.32, and what's that give you? So that gives you like 86%. Okay. B. Find the chances that a course has neither of these two requirements, and we already got that. That's 14%. Okay, find the chances of F given that it's R. So now you're only looking in this R region right here. So in the R region, the chances of its F is 32. 0.32 out of, in this entire region, there's 46%. So 32% out of 46%. And let's do it. I mean, I think it's easier looking at the Venn diagram, but let's do it just with the formula. Okay. So the chances of F given R are the same as the chances of F intersect R divided by the chances of it being R. So the intersection is given up here. Intersection is 32%, so that's 0.32, and R is research, that's 46, so that's 0.46. So look, it is the exact same fraction whether you use the formula or the Venn diagram, but the Venn diagram, it's just a little more, the visual helps, it's easier to see, but this is explaining the Venn diagram. Alright, find the chances that it's a research given that you're looking only in the final. So now this is the final world right here, and research is 0.32, so it is 0.32 out of 0.72. So 32% out of 7, and then simplify them when you're in business. Okay. Next, we are on 13 of 36 pages. So that's a pretty good chunk. Okay, problem number 100. A college finds 10% of the students have taken distance learning classes, 40% are part-time. Of the part-time students, 20% have taken a distance learning class. So look, the English is confusing. If they could just give me the probability, that makes much more sense. So let D be the event that a student takes a distance learning class, and let E be the event that a student is a part-time. Okay, so we're going to have to create our own. So the chances of D happening, looks like it is 0.10. Chances of E, what was E? It's part-time. E is 0.4. Okay, of the part-time students, 20% have taking distance. So this is kind of clever. This is pretty cool. So this is like going back to 3.1. Alright, what they're telling you that the chances of them taking a distance class given that they are part-timers is 20%. Alright, now there's no way to create a Venn diagram because we do not know the intersection. When you know the intersection, Venn diagram's a piece of cake. But I know this. So here's what I know. I'm going to go back to the formula. So I know my formula, probability of D given that E happens, is the same thing as the probability of D intersect E divided by the probability of E. Okay, now check this out. D given E, I know that, is 20%. And I know probability of E is 40%. And the intersection I do not know. So the probability is knowing the formula. Now it is algebra. So just solve for x, solve for the intersection. Times this side by 0.4, times this side by 0.4, pa-ching, pa-ching, you have found for x. And we are, is that 0.8 or 0.08? 0.4 times 0.2, 40%. Okay, that is 0.08. So now you know your intersection. Now you can make a Venn diagram pretty slick. Or you could just carry on with the formulas. So this one I'm just going to rock with the formulas. Here we go. Okay, let's do B. Find the chances of E given D. Chances of E given D are the chances of the intersection E intersect D divided by chances of D. And I know the intersection is now 0.08, and I know the chances of D are 10%. So 0.08 divided by 0.1. This is 80%. Okay, the chance of a union, so the chances of OR are going to be chances of D, add the chances of E, subtract the intersection of D intersect E. So chances of D are 10%, chances of E 40%, the intersection is not much, 8%, so 0.1 plus 0.4 minus 0.08, and we should get 42%. Okay, let's do D and E. D, using an appropriate test, show whether they are independent. Okay, I'm going to use this guy right here. So the chances of E are 4%. So the chances of E given that D should also be 4%, but they're 80%. So this is a big no. Are they mutually exclusive? That's a big no. Because of A, there does exist an overlap. There is an intersection, so they are existing at the same time. So that's a big fat no. Okay. 90. Look, that's the exact same thing as what we just did. You're gonna have to use a formula. You can't do Venn diagram. So we're gonna skip it to save time. So look that one up in the book. Go through it yourself. It is literally the exact same thing we just barely did. 87. Okay, let's go through this one. This one looks a little different. Special deck of cards has 10 cards. 4 are green, 3 are blue, 3 are red. When a card is picked, its color is recorded. An experiment consists of picking a card and then tossing a coin. So give me the sample space. So here's your sample space. You draw a green heads, or you draw a green tails. You draw a blue heads, or you draw a blue tails. You draw a red head, or you draw a red tails. Okay, now let A be the event that a blue card is picked. So probability of A is, it's got to be blue, and then it has got to go ahead. So the chances of you drawing a blue, there are 4 blue. Oh no, there are only 3 blue. 3 blue out of 10, and a head toss, you're going to times that by 1/2. So you got 3 out of 20. 3 chances out of 20. Okay, C. Let B be the event that a red or a green is picked. So out of the 10, 4 are red, 3 are green. So that is 7 out of 10. And then it's a heads, so that's 1 out of 2. So that is 7 out of 20. Oh, C. Are A and B mutually exclusive? Okay, so A was a blue and B was a red or green, so the answer is yes. There is no intersection. D. Let C be the event that a red or blue is picked. Okay, red or blue. So we got 3 blue, 3 red, so that is 6 out of the 10. By a head toss, that's 1 out of 2, so that is like 6 out of 20. Okay, now are these mutually exclusive? And okay, look, event A is blue cards, and event D is blue cards or red cards. So there is an overlap, and the overlap, so if I go red or blue, I got 6 out of 20. But 3 out of those 20 are blue. So the probability that C intersects with A is 3 out of 20. Because 3 of those 20 are blue. The other 3 are red. And these cannot be mutually exclusive because there is an intersection. Okay, we're on chapter 4, so I'm going to stop. Let's call it good for chapter 3.